So in movies, television, all around, we always see in shows, we see scientists. They're using DNA tests, they're using fingerprints somehow, and they're trying to figure out who committed a crime, who's innocent, and who's guilty. And that's a lot of chemistry. But how can we use physics to figure out who committed a crime and who's guilty? So forensics, this is the application we're going to talk about here today. Forensics is the investigation of crime using science. So in this case, we're going to be using physics, and we're going to specifically be talking about vehicular forensics, or forensics regarding the road and car crashes. So there's a lot of car crashes today. There's probably thousands, hundreds of thousands each year. There's a lot. And people need to know who's at fault, because they can be very tricky to understand and know what's exactly happening at every single moment. You need to do a lot of things to figure out who's guilty and who's innocent if there's multiple parties involved. So specifically, you can actually be using kinematics to figure out how far a car went, if you know specific the final velocity or the initial velocity, or if there's a video camera and you know, because there's a lot of video cameras, you can know how long someone was doing something. You can also use conservation of momentum if two cars hit each other, inelastic collisions, elastic collisions, and you can figure out, just by knowing the mass and the velocities they're going, you can figure out a lot of things about what's happening. Also, if a car is rotating or spinning around in a circle, you can even use rotational kinematics, which is very useful, and it's very similar to going straight forward with normal kinematics, but this is it can be used more in more specific cases. And also, you can even put in, with using normal force, the force of friction too, because you can know the force of friction of the road, of the asphalt, and you can actually calculate a lot of things also with the skid marks of cars. You can know where the cars were during specific collisions, if it was hitting another car or a person or even a building. You can know where they were hitting and how they hit it.
Here's a more specific example of vehicular forensics. So let's just say you have Danny, he's coming back from his grandma's house, and he's walking down the side of the street, right? But then all of a sudden, bam! We have Ryan, who's the reckless driver over here, unfortunately hits him, and Danny goes back a certain distance, and he hits the ground. So in this scenario, we have Danny, one of the objects, and Ryan's car, which is the other object. Ryan's car goes at a certain velocity to hit him backwards, while Danny goes to a certain displacement over a certain period of time. Using this lot of information, we'd be able to use kinematic equations to find exactly how fast Ryan's car is going, and whether he was exceeding the speed limit, which in this case is 5 miles per hour. Let's check out some math to see if he was actually speeding. Now let's look at this problem mathematically. Using kinematics, we have this equation. Delta x equals vi times t plus 1/2 a times t squared. And using this equation as well, Vf equals Vi plus A times T. We can substitute in A for Vf minus Vi over T. And we plug this in over here, we get this value. Multiplying everything by 1/2, we can put this over 2. Then we can distribute the T over here and with the 2T under it. And then we have this as a final equation, which is delta x times ViT plus T squared in parentheses multiplied by Vf minus Vi over 2T. Now, all we have to do is to add in our given values. We have 7 meters for our displacement, and 0.3 seconds for the total time to get to that displacement. Plugging in 7, we're going to multiply 0.3 by Vi, and plug in 0.3 for the time, square that, and our final velocity is going to be 0, with our initial velocity still unknown, and we're going to multiply the 0.3 times the 2. Then, using this, we're going to be getting 0.6, multiplying the whole equation by 0.6. Then we're going to be having 4.2 over here with the 0.18 Vi plus 0.09 times negative Vi. Then distributing this negative, we're going to have 4.2 equals 0.18 Vi minus 0.09 Vi. Afterwards, we're just going to subtract these two, and then we're going to get 4.2 equals 0.09 Vi, and we're going to use division so that Vi equals 46.6 repeating meters per second. Then, using our equations for the conservation of momentum, this as displayed over here, we're going to plug in 65 for Danny's mass, which is me, and we're going to multiply it by my initial velocity, which is 0, plus the mass of the car, which is going to be 910 kilograms, times the unknown of initial velocity, which is going to equal my mass times my velocity after the impact, plus 910 times 0. Then we're going to have this equation, which is 910 times vi equals 3,300.3 repeating, with our initial velocity calculated to be 3.3 meters per second. Then, converting this into miles per hour, we're calculated to get 7.38 miles per hour, and thus we were able to determine that at the 5 mile per hour speed limit, that this car was in fact speeding.
And so basically, in a traffic camera, you can just simply, by looking at the video, you can tell how far the car went, and using the timestamps on the camera, in what time. Using this, you can easily calculate the speed of the car, thus figuring out if they were speeding, how fast they were going exactly. Applications for physics and forensics, especially in vehicular forensics like we're using today. One example is calculating the speed using distance and time. Distance and time is easily found, especially nowadays that there are traffic cameras. Another example we can use for physics is friction and skid marks. Skid marks happen when cars stop, especially right before an accident, during an accident, collision. And so you can use, by knowing the coefficient of friction for the different road surfaces such as asphalt, which on a dry normal average day is 1, and on a day like today, which is very wet out, is only 0.2, you can calculate how long it would take in the car, especially looking at the darkness of the skid marks. Finally, you can also use inelastic collisions. Okay, so we have here momentum and the conservation of momentum. Momentum, P, equals mass times velocity. That's simple enough. The conservation of momentum states that the momentum in the beginning, or P of I, equals the momentum at the end, or P of F. As you can see this equation down here, we can use this equation in many different scenarios, such as car collisions. Here this states mass, obviously, so this right here is momentum of one object in the beginning, plus the other object, also, so the two that are colliding, equals the same at the end, but this time the mass and the velocities are going to be different. So we have a few different types of collisions. One type is elastic collision. In this case, it's like the game pool, where when you hit one car, in this case, when this car, is driving and hits a stationary car, it will hit it. Now, this car would have not moved, of course, and that car, the energy would have been fully transferred to the other car. Now, I have another one, inelastic collision, is when they stick together. So in this case, stationary, moving, the car goes like this, and they stay together. You can use this in forensics by you can figure out both of their speed at the end, and then reverse engineer to figure out how fast this car was going. One application of physics, forensics, can be used in other types of crimes other than just vehicular crimes. Another crime is gun violence. The bottom line is that physics makes the world a better place, and forensics cannot be done without physics. Thank you, Mr. Calvis, for teaching us the wonderful world of physics.